In this video, we are going to be taking a look at the fundamental theorem of calculus. We're actually going to be finding integrals using calculus for the very first time here. Basically, the fundamental theorem of calculus states that differentiation and definite integration are inverse operations in the same sense that division and multiplication are inverse operations. So for the first part, the fundamental theorem of calculus definition, let's take a look at what that has to say. If you have a function that's continuous on the closed interval a to b, okay, those are going to become what we're known as your limits of integration. And if you're looking at a graph, so let's say this is your graph, A to B, it looks like that. So if we want to find the area under the curve from A to B, that's your closed interval. We have to know that it can be integrable because it's continuous. And f is an antiderivative of the function on that interval, then what you would say is the integral of f of x is d of x is equal to capital F of b minus capital F of a. So your f of b minus your f of a, that's your upper limits minus your lower limit when you plug it into that function. So now that we have that, here are some guidelines on using the fundamental theorem of calculus. Number one, determine if you can find the antiderivative. Sometimes if it's not continuous, you can't even find the antiderivative. That'd be extremely rare, but it'd be a big waste of time as well. Number two, use the notation. So right here, the notation. This is the integral from a to b of your function is equal to capital F of x, whatever your new function is after you integrate, and then from a to b there. Sometimes I'll use brackets instead of that, so instead of that's a capital F, instead of just a line out front, what I'll do is I use brackets. It's the same thing. Either way, the a and b are the limits of integration. That would be the same as those a and b there as well. So it's upper minus lower. You plug in your upper limit minus your lower limit. And then lastly, the plus c is not necessary when you go through and do this. And I'll show you on the first one that we do down here. You can add that plus c, but it's unnecessary, and I'll show you why. So go ahead if you want to figure out what so this right here, this is your lowercase f of x. Figure out what your capital F of x is, and then come back to the video. Pause it. Now, like I said, I like to use brackets. It's a little cleaner for me. So here's your capital F of x. You get x to the third over 3 minus 3x plus c. And now you integrate from 1 to 2. So you would plug in your upper limit minus what you get when you plug in your lower limit. Go ahead and pause the video, try that, and then come back and see how you did. So I'm showing all of my steps. So when we plug in our upper, plug in 2, you get 2 to the third over 3 minus 3 times 2 plus c. Plug in your lower, you get 1 to the third over 3 minus 3 times 1 plus c. And then you just simplify from there. Don't forget to distribute that in. So that changes the 1/3 to a negative 1/3, the negative 3 to a positive 3, and that positive c to a negative c. And you can see right there that your c's cancel, right? So those are gone. And then when you simplify the rest of these all the way down, you get negative 2/3, which that represents the area under the curve of the function x squared minus 3 from 1 to 2. Okay, go ahead and try the next two. Try both of them, and then come back and see how you did. So let's take a look at part B. The first thing that we do, this 3 right here, this can be brought out front because it's a constant. So then you would square root of x, which is x to the 1/2. When we integrate that, you add 1 to the 1/2, which is like adding 2 over 2, and that's where the 3 over 2 comes from. Dividing by 3 over 2 is like multiplying by the reciprocal, and that's where this 2/3 comes from. And then I brought that 2/3 out front and multiplied by the constant of 3. So when I multiply multiply those together. That's where that 2 comes from. And then I plug in my upper limit. Now that makes it simple because now you just have x to the 3/2. So you plug in your upper limit and your lower limit. And that's where 4 to the 2/3 minus 1 to the 3/2, or sorry, 4 to the 3/2 minus 1 to the 3/2 comes from. And then 4 to the 3/2 is kind of tricky, but it's the square root of 4 to the third, and so that'd be 2 to the third, and that's where this 8 comes from right here. So then 8 minus 1 is 7 times 2, and we get 14. Okay, so a lot of algebra in there. You can see that finding the antiderivative, the integral, is not too difficult. Let's see how you did on the next one, the secant squared. The integral of secant squared is just tangent, because the derivative of tangent is secant squared, and that goes from 0 to pi over 4. So you can use brackets if you want to, since it's just one term. To me, I sometimes I don't, but you plug in your upper limit minus your lower limit. So tangent of pi over 4 minus tangent of 0. And that would be 1 minus 0, which is then just 1, and that's the area under the curve of secant squared from 0 to pi over 4. Absolute values. If you come across finding the integral of absolute values, I want you to look at the graph. Okay, so we're going to go ahead and graph this, the absolute value of 2x minus 1 on our little graph over here. Going to look something like this, and when we integrate from 0 to 2, that means that we want to find the area. So it would be from there to there and there to there, and you can see that you have two triangles. And so when you find the area of those two triangles, that would be then the integral. All right, so let's do the small area. So a sub 1. Okay, now actually, let's do it over here. A sub 1. Okay, we know that goes from 0 to 1/2, so it's going to be 1/2 times half the height. Okay, and the height when you plug in 0 is 1. Okay, we're plugging in the height of that triangle, and then a sub 2 is now, it goes from 1/2 to 2, so that would be a length of 1.5, and then times a triangle is 1/2 times base times height, and then the height of that is, we're going to plug 2 in right there, so that would be then 4 minus 1, which is 3. So that has a height of 3. Then we go ahead and simplify both of those. That would be an area of 1/4, and that would be an area of 9/4. So in total, the area would be 10/4, or 2.5 square units for that area. So looking at finding the integral of absolute value, definitely look at the graph when you do those. Now, sometimes you'll have areas that are bounded by several curves. So in this example, you have the 2x squared minus 3x plus 2, and that is identified as this function right there. And we want to find between the vertical lines x equals 0, so those in this case happen to be your boundary lines. Go ahead and set up your integral here, go through and solve, and then come back and see how you did. So pause it, try it, and then come back. Set up your integral with your limits of integration from 0 to 2. And when you integrate, you add 1 to each of these exponents and divide by that exponent, plus 1. And then this is 1 plus 1, and then that would be x to the 0 plus 1. And that's where it becomes x to the 1 there. And divided by 3, divided by 2, divided by, you could put divided by 1 there if you wanted to, but it's not, it doesn't matter. Then what we're going to do is we're going to take the upper limit, plug it in for our x values, subtract what we get when we plug in our lower limit. 0 is really easy because it's all that minus 0. So it's just really our upper limit that we're looking at. So you get 16/3 minus 12/2 plus 4, 16/3 minus 6/3, and you would get then 10/3. Okay, so all of that, the area under the curve right here, this is 10/3 units, whatever it is. Like that's usually a distance traveled, so it could be meters, feet, whatever that would be. The mean value theorem, again, it has to be continuous. Okay, that goes without saying on this interval. Then this part, there exists the C such that when you integrate right here, you get this value times b minus a. All right, now think about what that means in terms of, well, what is all of this? Well, it's the slope, right? So this integral represents your y sub 2 minus your y sub 1. So that's when you plug in your upper limit minus your lower limit, right? That's y minus y is equal to the slope times x minus x. It's very similar to, but now it's in the context of a calculus problem. And so that's similar to the mean value theorem for the derivative. The slope has of this tangent line, or the secant line, this would be the secant line, has a tangent line slope that's equal to that. So this is now just writing it as a integral instead of in algebra, or even like what we did when we looked at the derivative a while ago. Notice this can be rewritten, because what if I took and subtracted, or divided, not subtracted, sorry, divided each side by b minus a. So on the mean value theorem for integrals, don't write what's in red, because we're going to rewrite this in our next little part where it's the definition of the average value. I'm going to show you where the average value comes from. So we're dividing out a b minus a. So b minus a over b minus a, those cancel out, and you're left with the integral from a to b of your function dx all over b minus a. All right, now this, the definition of the average value is exactly that. It is 1 over b minus a times the integral from a to b of your function is equal to f of c. All right, so that's how you would find the average value of a function on the given interval. Okay, so this f of c, that represents the average height. Like if you're looking at the rectangles, okay, that will give you your average height of those rectangles. So average distance traveled given this speed. All right, so let's try this problem down here. The average value of 3x squared minus 2x on the interval. Go ahead and try this on your own, and then come back to the video to see how you did. So we set it up, and don't forget the 1 over b minus a out front. Otherwise, we do the exact same thing. So we have that 1/3, 1 over b minus a, always out front until the very end. We can multiply it, but then we're going to integrate it, and you would get 3x to the third over 3. 3x to the third over 3 minus 2x squared over 2 simplifies down to x to the third and x squared. And then you're going to plug your upper limits in. So plug 4 in, subtract what you get when you plug 1 in, and you end up getting 64 minus 16 once you simplify those down, and that would give you 48 minus 0, which is where this 48 came from, and then I multiplied 1/3 times 48, and we get 16. So that gives us the area under the curve from 1 to 4 on of the function 3x squared minus 2x. That's the average area under the curve, the average value, because of the 1 over b minus a. All right, so in the next video, we'll continue on, but that is it for this video.